thank you very much for the introduction, and thank you all for inviting me. So yes, as Marco said, I will be talking about two very different things, and the reason for that will be quite clear once I've briefly introduced myself. So I did my PhD at LPTMS, very close from here, with Christophe Texier and Satya Majumdar on applications of random matrices in different fields of statistical physics. So, for example, in quantum scattering, understand localization, cold atoms, and also different topics. And then for my postdoc, I moved to the Netherlands to join the group of Carlo Binacker, because Carlo is one of the world experts on applications of random matrices in mesoscopic physics and chaotic scattering. But now he's not anymore working on these topics, but he's more interested in topology and condensed matter, so I naturally joined all the projects going on in the group and try to learn new things. And so now I'm also working on these topics, topology, Majorana zero modes, and also still a bit on non-Abelian localization. But I keep working on both fields at the same time, so it's still both are active fields for me, and I will try to present the kind of interesting things I've been doing in these two directions in this talk. So, as I've touched many different things, it's kind of a bit difficult to see precisely all the things I've done, so I try to summarize all this in one picture, which I will use a lot in the following, and that's this picture. So, let me explain what's going on here. So the bubbles represent topics of physics in general, and the points here are my works, my publications. So you can see that it's a bit messy, but I've covered quite a lot of different topics. And although it seems like this from the distance, not really related, but there are actually some lines that connect all of them. So let me explain this. And I should say also at this stage that this is not meant as any realistic representation of any kind. So the size of the bubbles is not proportional to my interest in them or anything. And most of them should also probably intersect in one way or another. But I cannot represent this graphically in 2 dimensions, so I've just put the intersections that I considered. So I started my PhD up there in this field of quantum scattering, mostly interested on something which is called the Wigner-Smith matrix. I will discuss a bit about that later. And from there I moved to disordered wires, so which are some models interesting in the field of Anderson localization. And all these works have been done using kind of similar tools in the framework of random matrix theory. And towards the end of my PhD, I moved to a slightly different field, which is cold atoms. And the reason is that we can use some of the tools that I've been using up there in this field of by random matrix theory in this other field of cold atoms. So it's different questions, but the same kind of tools that we could use in these two. So that's how I jumped from here to here. And now, in my postdoc, I'm mostly doing now topology in condensed matter, and more precisely what is called non-Abelian anions, and I will describe this also a bit later on. And I've also, while in my postdoc, still kept working up there and in some stuff on Anderson localization. So that's kind of the global picture of my career up to now. And my goal is to explain some of these in this talk. So there are 2 main parts. The first one, which is mostly what I did during my PhD and kept doing during my postdoc, so on random matrix theory. And the second part will be some of these works here in topology in condensed matter. So let me try to go step by step to this picture, and I will keep coming back to this picture for the rest of the talk. So the first part is about the random matrix field. So it's a domain that was introduced almost a century ago, but it's still a very active field of research, and it appears in many different situations, and there are still lots of interesting questions related to it. And to try to give you the main ideas and types of questions we are looking at in this field, let me introduce it through the important historical example, which is the first application in physics, which is in nuclear physics. So the big problem in nuclear physics is that the atomic nucleus is a complex many-body system of strongly interacting particles. So So it's very difficult to study analytically. And the idea of using random matrices is to simplify this problem. So it's a different idea that was introduced by Wigner in the 50s. And it's to switch from the microscopic description to a statistical description. And in this case, you cannot ask the same type of questions as you would when you have a microscopic model. So you have to change the nature of the questions to focus only on universal properties. So let me give you quickly an example of what I mean with this. So this is a picture obtained experimentally of the spectra of two different nuclei, so thorium and uranium. So here it's the energy. It's a picture obtained by neutron scattering. So when you see a peak here, it means that the nucleus has some energy level at this energy here. So if you look closely at this picture, you see that, of course, there are differences. So for example, here you have an energy level here, but you have nothing here. So this is normal because there are different systems. But if you step back a bit and look globally at this picture, you can see that they roughly look the same. You have some peaks which are never very close to each other. There's still some spacing between them. And so maybe you could try to give a statistical description of the distribution of the levels, but you cannot, in this case, predict precisely where the levels will be located. So that's kind of the idea. Now to make this more precise, to do what we are actually doing to do this, is to replace the exact microscopic Hamiltonian by a random matrix. So this is an idea which is kind of similar to what you do in statistical physics, when instead of describing all the positions and momenta of particles in a gas, you instead give yourself a probability over the microstates. Here it's the same thing, but you, instead of constructing the microscopic Hamiltonian, you give yourself a probability measure on different Hamiltonians. And this Hamiltonian has to satisfy the basic symmetries of the system. And that will be the only important point here. So Wigner and Dyson considered three symmetries, which is a time reversal symmetry. In this case, it imposes a constraint that this Hamiltonian must be a real symmetric matrix. You can, if you break the time reversal symmetry, there is no additional constraint than the fact that it is Hermitian. And if you break spin rotation symmetry, you fall in another symmetry class, which you can represent by matrices of quaternions. And these classes are labeled by this index, beta, which is called the Dyson index. And it basically counts the number of independent real components you have per matrix element here. So, for example, if beta equals 1, it's a real matrix, so one component. Beta equals 2, it's complex, 2. And 4, it's 4 quaternionic matrices. So that was our three original symmetry classes. Now there are more symmetry classes which were introduced at the end of the 90s by Atlan and Zellbauer, which come from the consideration of two other symmetries which you encounter in QCD and in condensed matter, which are particle hole symmetry and chiral symmetry. And that gives you now 10 symmetry classes. But at this stage, let's focus only on these three for simplicity. Now, once you say, okay, you will take this Hamiltonian to be random, you have to choose from which distribution you pick your Hamiltonian. Now, at this stage, it's a choice, so you have the freedom to pick any distribution that you like, because you keep in mind that you want to focus on universal properties, so it should not depend too much on the details of the distribution that you choose. So the simplest choice you can do is to pick the matrix elements to be independent and identically distributed Gaussian variables, which are either real, complex, or quaternion. And in this choice, it's very convenient because then you can write the probability of picking this matrix as the product of all the Gaussians for all the independent elements, which factorizes into this very nice form. So the prefactor is kind of arbitrary also. And it factorizes a trace of h squared, because you can see that if you expand the trace of h squared, you get the sum of all hij squared, and it gives you again the product of all independent variables. And in this form, you can see that this distribution has a very nice feature, which is it is invariant under change of basis. So if you multiply on the left by a unitary matrix, on the right by its inverse, it's the same weight here. So this is an important feature, which you find in a more general class of ensembles of random matrices, which are called invariant ensembles. which you can generally write in this form as exponential or minus trace of some function of the Hamiltonian. So in this case, this function, which I called v, was h squared, but it can be anything you like. Now, the very nice property of these invariant ensembles is that because it's invariant on a change of basis, you can decouple the eigenvectors and the eigenvalues and focus only on the eigenvalues, which are usually the quantities of interest. For example, in the previous case, it was the energy levels of the nucleus. And you get, quite generally, this kind of joint this probability distribution for the eigenvalues. So you have this last term, which is the product of, which is the product coming from this form here. So if you had only this, it would mean that the eigenvalues would be independent and identically distributed with this probability weight. But you get additionally this term, which is a Vandeman determinant. And that term comes from the Jacobian of the change of variable from the matrix entries to eigenvalues and eigenvectors. And this term here induces correlations between the eigenvalues. So you can see it clearly that if two eigenvalues become very close to each other, this becomes very small and this probability vanishes. So you have effectively a repulsion encoded in this distribution between the eigenvalues that you cannot have two eigenvalues close to each other because of this term. And that's a very central element in random matrix theory. So now, so all of this now is our starting point. So we have picked a probability distribution from the Hamiltonian. It gives you this joint distribution of eigenvalues, and then the questions you ask depend on the kind of physical quantities you are interested in or the context. So for example, the typical thing you can ask is what is the mean density of eigenvalues? So here I show you the example from the Gaussian matrix which I showed before. That's a histogram of the diagonalization of one big matrix. And the red line is the famous Wigner semicircle law, which is the mean density for this type of matrices. Now, the other kind of thing you can look at is correlation, because I have said the eigenvalues are correlated because of this effective repulsion, and you can try to study what are these correlations. Now, related to this, and which is one thing which was important also historically, is the spacing between the eigenvalues. So you look at the distribution of the distance between one eigenvalue and the next, or one energy level and the next. And that was important in the field of nuclear physics. So here it's a very famous picture. But the histogram, I don't know if you can see it clearly, it's a histogram of almost 2,000 spacing of different atomic nuclei combined together, which gives you this histogram here. And if the energy levels of these nuclei were independent random variables, you would expect to have a Poisson distribution like this. But you can clearly see that this is absolutely not the case, and you have a distribution which fits perfectly the prediction of random matrices, which is here. So this is a very famous picture which you have probably seen before, and even you have seen it in the beginning of the talk because it was on the logo of the IPhT-TV. So and the last type of things, not last type of things. So many works also have been done on extreme value statistics, so largest or smallest eigenvalue, so what is the energy of the ground state, for example. And the thing I've focused on the most is called linear statistics. So there are quantities which take this form here, sum of a function of the eigenvalues, which you can write also as a trace of the function of the matrix. And these appear in many different situations and play a very important role in many different applications in physics, and I will mention a few of them later on. So now, this was kind of motivated by originally by nuclear physics, but now there are applications of random matrices in many different fields. So for example, here I list a few in mathematics or in where I'm interested in physics here. So there's also nuclear physics. I've worked on quantum transport. There is also quantum information, spin glasses. I've slightly explored cold atoms, and also in statistical physics I've looked at some applications here. So I will briefly describe a few of them in the following to give you quite of an overview of the questions I've been interested in and the type of problems I've encountered. So let me start with my original interest in this field, which is on this so-called Wigner-Smith matrix in the field of quantum scattering. So let me introduce what is this field. So quantum scattering you study, it can represent the scattering of an electron by a quantum dot, for example, here, or by a disordered driver. So you send an electron inside and you look at what comes out. So it's kind of a natural thing to do. For example, if I give you a quantum dot and you want to have some information about it, what you would do, you would plug it to some macroscopic devices, try to make measurements, and that's what you do here when you send an electron and look at what comes in. Now, in this field, the central element is the scattering matrix, which tells you what is the amplitude of the wave coming out, given the amplitude of the wave coming in. So this matrix is unitary, because you have conservation of the number of electrons that you send inside. And it must also satisfy different symmetry depending on the symmetry classes that I mentioned before. Now, in the example I was discussing the introduction in nuclear physics, the central matrix is the Hamiltonian, but in this case, the central matrix is the scattering matrix. So here, instead, we will focus on this matrix and replace it by a random matrix, as we have done before with the Hamiltonian. And then we have to make some assumptions on the distribution of this matrix. So for example, we can take it to be uniformly distributed over the unitary group. So although this is the most important matrix, there is another one which has attracted a lot of attention, and this is the Wigner-Smith matrix, which I have discussed, and it's constructed from the energy derivative of the scattering matrix. And this matrix encodes temporal aspects of the scattering process. So it tells you how much time the wave packet that you send inside will stay here before coming out, something related to it. And this matrix is very important in when you want to study dynamical properties of this kind of systems.
So the epsilon is the energy of
Is the energy of the wave that you send inside. Yeah. All right, so let me mention a few things I have done about this matrix. So there have been lots and lots of works on studying the transport properties of a quantum dot in equilibrium. So for example, you connect two leads and you apply voltage difference and you measure the current going through, which gives you access to the conductance of the quantum dot. But if you want to study other properties like capacity or kind of things, you need to do some to study the dynamical response. So you have to apply an AC driving, and that's, in this case, the simplest kind of setting is a RC circuit that you make from the quantum dot. And it's actually some experiments that were done at the ENS in Paris, where you take a quantum dot and you put a grid on top of this to make some kind of microscopic capacity. And you study the impedance of this circuit, which for low frequency takes this form here. You can extract the capacitance and some charge relaxation resistance, which gives you related to the time you need, well, the time the charge you inject will stay inside before leaving. And these objects are related to the trace of the Wigner-Smith matrix I mentioned before, and the trace of the square. And so what I have done was to study the joint distribution of these two quantities to try to get some information about the statistical distribution of this impedance. And this was done using a result for the distribution of this matrix Q when the quantum dot is perfectly coupled to the exterior. This is a famous result by Bauer, Fram, and Binacker in the end of the 90s. So now what I have done towards the end of my PhD thesis was to extend this result to the case where you have not perfect coupling between the quantum dot and the outside. And in this case, we have obtained a distribution for the matrix, which is more complex than the original one, of course. It looks a bit heavy, but we have actually been able to use it to study also this same object, the trace of the Wigner-Smith matrix, which is important in many situations. And more recently, I have extended this, again, this famous distribution in another direction, by this time considering what happens if you have absorption in the system. So it's important, for example, in optics, if you look at a cavity, your photon inside can be absorbed at some point. And so I have obtained now, very last year, the distribution of this matrix in the presence of absorption. So I have new extensions of this distribution, and I would like now to use them in the future to get results similarly to what has been done before from the result of Wolfram and Binaker between these new situations where you have absorption or not perfect pattern.
Can you say just a few more words about what you mean by perfect coupling or not perfect coupling?
So yes, when you have your quantum dot, and you want to connect it to some lead, which is just a waveguide in which some modes propagate, and then you can have some probability of, when you connect these two, you can have some probability that your electron is going to be reflected directly without entering. Yes, and this of course will change the dynamics, well, the scattering matrix, because then it will not even enter in this region. So that's. So it's the distribution of the Wigner-Smith matrix that we start here from, that we take from them. We assume the distribution of Q. Yes. Yeah. Well, no, they have proved it at the end of the 90s. Yes, exactly. Yeah. In this case, it's yes. Yes, it's in this case the inverse of Q is a Wishart matrix. So it's like a gamma distribution but for matrices. Okay. And that's the result I have extended to these two cases to get new distributions which are more complex. Okay.
Clarify what you mean by what can you say a bit more about the link between the distribution of Q or the trace of Q square and the impedance? Meaning in this impedance is very important, as you said, one over omega part of capacitance,
Yes.
then there is the one more
Yes.
impedance. So is there
Yes, there is.
a link?
So this C is directly related to the trace of Q, or 1 over C is a trace of Q. I'm not exactly sure, but it's a direct connection.
Okay.
And
What about the Q dependent, the epsilon dependent? Is the Q dependent on epsilon? I guess.
yes, but you work always at a given energy, and then
The epsilon dependent is not the omega dependent.
no, no, no. The omega is no, it's the frequency of what you
That's when
yes, yeah, the frequency of the driving that you make. Yeah, and then if you want to know, RQ is a trace of Q squared divided by the trace of this squared. So it's so you need the joint distribution to study this part. Okay. Yep. So that's the first part on quantum scattering, and as you can see, I've studied a lot this observable trace of Q. Also here I started to do some work, and it appears also in a different context in disordered wires. And in this case, the trace of the Wigner-Smith matrix is related to the density of states of the wire. So you can understand why it's an important quantity. And then I have developed a new tool compared to the one that we were using before to study this new observable, because in this case it has infinite moments. So even the mean is already infinite, so it leads to more complications. And so we have obtained the distribution of this trace, which is called the Wigner time delay, using another distribution which was also derived by Bauer and Binaker for the distribution of Q in this case. Right. Now, these models of disordered wires, they were introduced in a very different context, and it's about Anderson localization, because it's they are very nice models in the sense that they are not exactly 1D, so you get more rich phenomenology that you have than you have in one dimension, but it's not yet 2D, so you can do more things analytically than you would in higher dimensions. So they were introduced in the 80s by Dorokoff, Meadow, Pereira, and Kumar, which gives the name DMPK for the approach that they use. And then this approach was extended to the new symmetry classes that I mentioned before in the beginning of the 2000s, because then it allows to study, for example, superconducting wires and these kind of things. And all this approach is based on very strong isotropy assumption. It means that all the modes that propagate inside here, that you can think of, if you have no disorder, you can think of the waveguide, you have different modes propagating. And their assumption is that they are all equivalent, and they all couple together by the disorder. So it's a very strong assumption that it basically makes you stuck in this quasi 1D geometry and cannot take into account more spatial dependence in the other direction. And we have done some work to start to go beyond isotropy in this case, so to extend the approach of the MPK to more to take some non-isotropic disorder between the channels. And in this case, I have obtained a new matrix model, which is this time is not invariant. Unlike what I have said before, which at the beginning of the talk, when you were looking at invariant ensembles where the eigenvalues and eigenvectors decouple, it's no longer the case in here for this model. And that's because you have not isotropy between the channels. And I've been able to study density of states and also some topological properties, because these wires became again popular more recently, because you can study in them the effect of disorder on the topological phases of matter. So you can see that the strong disorder can drive topological phase transition, which are transition between two phases, between two quantum numbers of topological origin. So I will not discuss this more here, but all right. So this is basically the first half of my PhD up to now. And towards the end, as I said, I moved a bit to cold atoms because we have the same type of questions and same type of tools that we can use in this field. So I will mention it because some people here are working on related topics and could be interested. And the basic idea is that there is a direct connection between non-interacting fermions and random matrices, which is the following. So the position of non-interacting fermions in a harmonic trap in one dimension at 0 temperature, so in the ground state, can be directly mapped onto the eigenvalues of some random matrices. So then you can use the tools that I've been working a lot with in random matrices to study this system of non-interacting fermions. And although they are non-interacting, it's not so trivial because of the Pauli exclusion principle. There are some correlations which could be difficult to handle and which we can do with the tools of random matrices. Now, this connection holds at 0 temperature, but you lose it when you go take into account the thermal fluctuations. But there are still some connection with mathematical objects which are related to random matrices that are called determinant point processes. And I have used this to introduce a method to study any linear statistics, so which can represent wide classes of observable, for this system at any temperature. And I have used it to study the number of particles on the positive axis. So what is the number of particles here, and how does it fluctuate? So I looked at the two first moments, and I have looked at what happens in the case of canonical or grand canonical ensembles, because so we know in statistical physics that the ensembles are equivalent in the thermodynamic limit, but this holds only for average quantities. So when you look at fluctuations, it's important to know in which ensemble you work. And in these systems, the canonical ensemble is probably more relevant than the grand canonical ensemble, but it's of course more difficult, because then you have some correlations between the occupation numbers of the different energy levels, which are independent in the grand canonical case. And this led us to study general correlator of different occupation numbers of different levels in another paper here. All right. So that concludes mostly my first part on this big random matrix part. I will not discuss what happens here in Anderson localization. I spoke about disordered wires already. There are some works that I did recently, which are probably this one, which I will not talk because it's a bit of a singular point in this graph. So I will mostly now move to the second part about topology in condensed matter, if that's fine. So let's start with this, and let me discuss what are these non-Abelian anions that I've been working on. And for this, I have to come back to the very basic properties of quantum mechanics, which is what happens when you have indistinguishable particles. So imagine you have two identical particles. You can represent the state of the system by a quantum state, which puts one particle at position x1 and the second one at position x2. And now if you exchange the particles, the physics should be the same because they are indistinguishable. So it means that the state should be the same up to some phase. Now to determine what is this phase, you can do this exchange a second time, and you pick up twice the phase. Now this double exchange is equivalent to taking one particle and moving it around the other. And now, the situation depends on which dimension you are. So usually for fundamental particles you are in 3 dimensions. And in this case, so you can deform this path because the result should not depend on which path you choose to move this particle around the other. And in 3 dimensions, you can take this path and make it move above or below this particle and reduce it to a trivial path where you have not moved the particle at all. So in this case, it means that this state must be exactly the same one as here, including the phase. So this phase in 3 dimensions must be 1. So it leaves you 2 possibilities. So either this theta is 0 and you have bosons, because when you exchange 2 particles, the state is the same. Or this phase is pi, and so when you exchange the particles, you pick up a minus sign, so these are fermions. But if you work in lower dimensions, so in 2 dimensions, then you cannot reduce this path to a trivial path, so these states have no reason to be related in any way, and so you can have any phase that you want between 0 and pi. And these particles which have any phase here are called anyons, so it just comes from any, and you put ones at the end. Now, these are not exactly the things I was mentioning, so I was talking about non-Abelian anyons, which is a bit more complex, and they appear typically in systems where you have, from your Hamiltonian, you have degenerate states, and then when you take, still in 2 dimensions, one particle around the other, you can have a non-trivial transformation within this degenerate subspace. So this means that when you start from one given state here, after doing this, you can end up in a superposition of all the states. So it means that you apply this matrix here, alpha, and because matrices in general do not commute, if you make several operations like this, there is no reason that the output should be the same. So therefore it's called non-Abelian anyons, because matrices in general do not commute. So yeah. So these are the type of quantities I'm interested in. And to try to make things a bit more concrete, I will introduce the example on which I have been working on a lot, which appears in Currents Matter. And at this stage, it might look a bit formal and arbitrary, but let's just stay with me for a minute and you will understand what I want to say. So imagine that you have 2 fermionic modes, which are called A and B, associated with creation and annihilation operators, which satisfy the usual anti-commutation relations. Now you can formally write them in terms of 4 Hermitian operators, which are called gamma 1, 2, 3, and 4, by separating the Hermitian and non-Hermitian parts. Now it's like cutting a complex number into real and imaginary parts. And you can check that these gammas from this commutation relation should also anti-commute, but square to 1, because now they are Hermitian. And the claim is that these gammas are non-Abelian anyons. So here, it's, as I said, it's a bit arbitrary to say that we introduce these operators from the fermionic modes, but actually what happens, what you should keep in mind for the following, is that the non-Abelian anyons that I will consider will be of this form, so you can take 2 of them to create a fermionic mode. So they always come by pair, and in a pair of them you encode the fermionic degree of freedom. So that's the way to think about it if you want for the following. So what I want, yes?
You're going to add some number, internal quantum number to this to make it better possible, or how do I see that?
So,
you know what I mean?
yeah.
Is that some,
That's my next slide.
okay.
So yeah, my point now is to try to show you, starting from this, that these are indeed non-Abelian anyons. And in order to do this, let me introduce just some basis of my Hilbert space, because I want to show that when I make an exchange, I change the state of the system. So I will start with a basis. The natural one is the occupation basis of these 2 fermionic modes. So it's either A is empty or occupied, or B is empty or occupied. And actually, instead of looking at the states, what will be more convenient is to look at the parity operator. So these states are eigenstates of this parity operator, which is simply expressed into these gamma i's. And so this state has parity 1, and this state has parity -1. So this operator just gives you the parity of this number here. And using this, I will show you now that these objects are indeed non-Abelian anyons. So the situation is the following. So we have these 4 objects here on a plane because we are in 2 dimensions. We cannot have this in other dimensions. And let's assume that we have that the fermionic state encoded by 1 and 2 is empty, and the fermionic state encoded by 3 and 4 is occupied. So I'm in this configuration. Now here I draw branch cuts. So this is more convenient because in the following I want to make an exchange, and keep in mind that these operators anti-commute. So when I exchange 2 of them, I should pick up a minus sign, and these branch cuts are here to help me to see when do I pick up a minus sign. So if a gamma crosses a branch cut of another gamma, it will take a minus sign. So now what we want to do is to make this exchange. So take gamma 2, move it around gamma 3, bring it back, and see what is the state of the system now. So you see that when you take gamma 2 around, it will first cross the branch cut of gamma 3, and then when you take it back, gamma 3 will cross the branch cut of gamma 2. So they both pick up a minus sign, and the other one remain unaffected. So when you do this, you have gamma 2 going to minus gamma 2 and gamma 3 going to minus gamma 3. So if you remember, the parity of A is I gamma 1 gamma 2, so it goes from its value to minus its value. And the same for parity of B, it changes sign. So here before I had a state even odd, and now here I have a state odd even. So by simply moving this object around this one, I have changed the state of the system. So this is the signature of a non-Abelian anion that I was describing before. And you can write what is the matrix that you should apply to switch when you make this exchange here, and simply a parity switch, so it's expressed in terms of this 2x2 matrix. So these objects are indeed non-Abelian anions. Now this signature is called braiding because you have to track the braiding of these word lines to see what is the result, and so that what this name is that this is what I will use in the following when I talk about exchanging particles. I will say braiding instead of exchange, but it's the same idea. All right, now there is another signature of these non-Abelian anions, and it's called the fusion rule, and I want to introduce this because it's important in my work. So let's come again to that setting. I have my 4 gammas, and this time I take them into both empty states here, 1, 2, and 3, 4. So even parity. Now I have coupled them like this, but I mean the idea that you can take 2 of them and combine them together to create a fermion, a fermionic mode. So instead of pairing 1 and 2 and 3 and 4, I can pair them in different ways. So for example, I could take 2 and 3 together, or 1 and 4 together, and ask what is the state here of this new fermionic mode. And if you do the computation, so you introduce a new basis which is made of new fermionic modes alpha and beta, made by combining 2 and 3 and 1 and 4, and you can show that this state, which was 0, 0 in this basis, becomes an equal weight superposition of 0, 0 and 1, 1 in this new basis. Meaning that when you bring 2 and 3 together, you can get either a fermion or nothing with equal probability, and you will get the same result if you pair gamma 1 and 4 together. So that's called the fusion rule, that you get this equal weight superposition of even and odd parity. And sometimes denoted like this, which kind of recalls the combination of the angular momenta, 1/2 plus 1/2 equals 0 plus 1. It's kind of the same idea. Here when you bring 2 and 3, you get either the identity, which means nothing, or a fermion. So if you see this, that's just the fusion rule here, which says equal weight of these 2 possibilities. All right, so I've talked now quite a lot on these abstract things, but people have been interested a lot in these questions over the last few years for different reasons. So first of all, well, it's interesting to study unusual statistics, which are not fermionic or bosonic. But the main reason is that this could be used to realize topologically protected quantum computing, in the sense that because 2 of these gammas encode 1 degree of freedom, and they can be far away from each other, it's a non-local encoding of 1 degree of freedom, so it's kind of protected from local perturbations. So it should be more robust than any other thing. And you can use them to do quantum computing, because your qubit can be encoded in the parity, 1 and -1. You can switch the parity by doing braiding, by exchange, because that's how you change the state. And you can measure by the fusion by putting the two of them together. And that's one of the reasons for the lot of excitement around these objects. So now let me say where you can find them, because this is a nice story, but they should be realized somewhere, one way or another, in physical systems. So they cannot be fundamental particles because they are only boson or fermions, but you can hope to find them as collective excitation in two-dimensional systems, and so condensed matter is a natural place to look for them. And there are two main possibilities. So there are quasi-particles in the quantum Hall effect. And the other one, which is more recent, is vortices in topological superconductors. And that's the kind of thing that I have been mostly looking at. So let me just say a few words on what I have done on this field. So there are proposals to demonstrate the fusion rule experimentally. So it's the idea of taking two of these non-Abelian anions and bringing them together and seeing this equal superposition of even and odd parities. But the problem is that there are many other things that can reproduce the same output, even if you do not have these non-Abelian anions. You can have other levels which pollute you and produce which would be occupied or not. You can have degenerate levels by accident. And what we have done is to build up on these proposals to identify when you can actually say that you have this non-Abelian statistics. So in this case, it's called Majorana zero mode, if you have seen that before. And so we have found a way to say whether you have actually topological state, which non-Abelian statistics, or two states which are accidentally degenerated and which produce the same output of zero mean parity. So this is the first part of my work. And the second part is something slightly different, because the main problem with these vortices in topological superconductors is that they are fixed. They are bound to a defect, and you cannot just take one and move it around easily, which is what you would like to do when you make the exchange. So what we have done is to look at other types of excitations which have non-Abelian statistics, and they are called edge vortices. In this case, so I will not go into much details, but the idea that in this paper they introduced a way to create on demand these excitations which have non-Abelian statistics. So just by applying a voltage pulse, which is kind of a needed thing to do. So you can create them whenever you want, and the advantage is that they are propagating. So when you make this voltage pulse, you create a pair of these edge vortices here, which then will propagate towards the right. And it's a similar idea to the very popular one of flying qubit, which you have maybe heard about when you encode a degree of freedom in the charge of the net state of a quantum Hall effect. But here it's the same, but you encode the parity, which is protected because it's a non-local object, in the pair of edge vortices which propagates. And then you can hope to try to realize some things with that. And so what we have done is to introduce possible setups to obtain signature of braiding of the exchange and fusion simply by measuring the current coming out of the device. So you make a voltage pulse to create these objects when you want, and you measure the current coming out, and you should see the effect of the non-Abelian statistics in the current coming out. So it's kind of an easy measurement because you can apply voltage, and measuring charge is the most easy thing you can do. And we have studied analytically effective models of these setups to show that indeed when you apply the voltage pulse, you obtain the result that you expect from the non-Abelian statistics of the objects without putting them by hand. That's kind of, we have the two parts of the story that is a hand-waving argument when we say we inject particles which have non-Abelian statistics, and the actual derivation when from the Hamiltonian of the system we can show that what we do when you apply voltage pulse leads to an output which is what we expect from this argument of non-Abelian statistics. So we do not put it by hand, but we start from the Hamiltonian of the system. All right. So I hope that this gives a good overview of the different topics I've covered. And I will just briefly talk about the things I would like to do in the future. So I would like to keep working on the two directions I've been working on in the past, so random matrices and topological states of matter. So in random matrices, I have some ideas still in this field of quantum scattering with the Wigner-Smith matrix. As I've mentioned, I have obtained new distributions which I would like to study more to see what are the physical consequences of absorption or these kind of things. And I also have, I'm so now working on something in the disordered wires related to this matrix. Now, here it's a field which I have been working on for only 1 year, so I have much less experience to know what is interesting or not, but these non-Abelian statistics are quite an interesting thing. And I know that, so I have only covered the topological, the superconductive part, but I know that here you have experts in the quantum Hall effect where you can find other of these objects, so I would be interested to know a bit more about this. And I would also like to explore new directions, mostly in non-equilibrium statistical physics. So here it's also a field that I do not know a lot, so I would hope to be able to interact with some of you to find new directions. So for example, I mentioned the time evolution of quantum systems or quantum quenches. And there is one direction which I know I could start from my experience in random matrices, which is the KPZ equation, because there are connections between random matrices and this equation, so it could be a natural entry point. So I don't know if you want me to say a few more words on this part, but otherwise I can just conclude. So if you have more questions, I can explain you what this is, but this, I hope now you understand what this means. As it's a nice summary of my research. I would hope to expand this to put more points in different places and maybe new bubbles somewhere in the future. So, thank you. Of course. So, KPZ equation was introduced to study the evolution of an interface between a stable and a metastable phase. So, here I show actually examples in a very nice experiment where you have a liquid crystal here, which is in a metastable phase, and you put a small perturbation in the middle, and which creates a stable phase, which then grows and grows and so on. And this is the equation that they wrote to describe the evolution of the height. So from the center here, this is the height of the interface h with time. And so it's a stochastic equation. You have a noise term here, and you have a nonlinearity, which makes this equation non-trivial to study. And actually, what people have shown is that in the long time limit, the distribution of the height of this interface actually corresponds to the very famous distribution in random matrices, which is the distribution of the largest eigenvalues, which is in different symmetry classes. You can see from the experiment, it also matches pretty well the prediction of random matrices. Now, there have been lots of works in one space dimension and one time. So this 1D interface here, or here, which is flat, where people have looked at small and large time distributions. So there are also exact results which are kind of complicated, so it needs some work to extract some information. And there is this connection with random matrices. So now in the future, people could ask what happens in intermediate times. Could we have some similar results with using random matrix tool to get other models in the KPZ class? And I know some recent works where people have obtained some similarities in the distribution, so something I found myself in random matrices. So maybe this could also be another clue at what is this connection between KPZ and random matrices, because for the moment it's just the fact that we have the same distribution, and that's all. So this could help to understand what is this connection between the two. So. Yes. So the idea that you inject this pair of vortices in a definite state. So let's say that when you fuse them together, you get nothing. Now, if you do braiding, you will change this, and you will get one charge coming out, because you have changed the state of the system from nothing to creating one fermion. So that's how you see that you have done braiding, because if you start from nothing and you get an electron, then you have changed the state in between. And the fusion is maybe more simple to understand, because so you remember we have two pairs and we mix them between pairs and we get even superposition of even odd correlated. So here, this setup, you inject one pair here and one pair here, and then this one comes to mix with the one of the other pair, and same here. So you should so sometimes you get nothing, sometimes you get an electron, but it's either nothing, nothing, or electron, electron. And we have shown that when you do the computation of what happens when you put the voltage pulse, that you get that the average charge is E/2 coming out of both leads, and the variance of the difference is 0. So this is the signature of the fusion. Mm-hmm. Yes. So there was one. Wait, let me think. I forgot the name. Probably. So it's very different model of interface when you do not have the non-linearity. I mean, I might be wrong, but there is a well-studied model which name escapes me at the moment. But I'm not sure if it's for this stable, metastable thing or not. But there are different models, and this one is maybe the simplest one, which has interesting behavior, and it's has a huge universality class.
Yeah.
Yeah. So I like a lot, well, a recent one, which is the one I've done on myself, because I mean I've done all of it on myself and I wrote the paper myself, so it feels a bit special compared to the other one, so it's probably this one. And I found also, so I will cite just two more. I liked a lot the one on the disordered wires, on the non-isotropy, because it was very nice work on when you have a stochastic differential equation for a matrix and not just for eigenvalues as usually, and which we were able to solve to find the stationary distribution analytically, which is quite nice. So I like this one a lot for the technical part and the beauty of the thing. And I mean this recent one, this last one here also is quite fun, because before in this paper and this one we were doing adiabatic thing, so we did not have any time evolution or anything. But in this last one we were able to solve the full time evolution and to see the vortices being injecting, propagating, and we can play a bit with them by delaying them and so on. So it's quite fun. Mm-hmm.
Okay.
Thank you.